Huh?
Oh, the camera was facing the door.
Oh,
so
yeah.
I know.
That's good enough.
Oh, okay.
I think so.
Oh. You bring this copy?
Huh?
Just kidding.
You gotta market those bottles.
Oh, yeah.
US patent number?
That's right.
I will say. Oh, well, sure.
Let's see if I wrote it down. The latest issue, I believe, is Spectrum. It's a monthly magazine, so the October
So-
issue of it is all blockchain.
What are the benefits of a packet switch network?
Well, you didn't have like no setup time. It's just like, and packet is independent. So if the one packet is lost, it doesn't have to. You have to retransmit the whole.
You don't have to retread it?
Yeah.
So if we have packet loss or some kind of error in the middle of a data stream, we only need to retransmit that one packet.
And
What
if
else?
we have routers down, then it just if you packet that just queued, if the router has to be transmitted, not the whole thing.
Correct. So what,
Shit.
before we go on to disadvantages, if you have a modern network that has a number of devices that are interconnected with each other, and very rarely does one device directly talk to another device. In that circumstance, is there another advantage to a packet switch network?
They can take different routes.
They can take different routes, but also consider if you set up a circuit inside of that, and nothing is segmented into packets.
Can you repeat the question again?
So if you have a modern network,
Devices are interconnected.
and you have a modern network where the devices are interconnected, right? Am I very familiar by now? So one of the things is they can take different routes, right? But let's say for whatever reason our routing picks this route right here because it's the most direct. In this circumstance, do packets give another advantage to the network? Let's think about how things actually work in the network. Right? So packet goes across the network, right? And in reality, it's most of the time as wide as that network for all the reasons that we talked about, right? So it goes across the network. What happens at this device? Right, there's a fabric in there, right, with buffers. So the packet enters this device and then is retransmitted along this line, right? When is it retransmitted?
Oh, you're talking about the store and forwards?
Yes.
Yeah. So it's basically once it receives the whole packet and make sure it's correct, then it's forwarded.
Yes.
Yeah.
So what happens if we didn't fragment our packets?
Well, if we didn't receive it within the amount of time we're gonna ask for it, at the timeout, the time expires, basically that drop it.
Yeah, so we could get a timeout, right? Normally our packets are as wide as the network can be, right? What if our packet was much, much longer? So in a modern packet switch network, right, the time of a packet entering this device and being stored to this device and then forwarded to the next device, right, is relatively small, right? It's because our packets are small. If our packets are large, what happens?
You gotta wait.
We gotta wait a really long time. In fact, we have to wait for the entire message to make it across the network, right, to the first device, and then gotta wait for the next message to make it. Essentially, what we have to do is wait, in this particular network, we have to wait 3 times the amount of time that it took to transfer. Because we're essentially transmitting 3 times, right?
Why we have to wait 3 times?
So if we send the entire message rather than having it fragmented as packets, right? So the time to transmit here is whatever the length is, right? So let's just call that 1. The
Okay.
time to transmit here is 1, the time to transmit here is 1, so our transmission time is 3. If we do it packets, right, then the transmission time is the amount of time it takes from here to get to here, plus any switching time inside the device, plus the length of the first packet. And that's it. So while this one is 3, this one will come out something close to 1. Because each of these are coming 1, but the second packet is traveling this length as the first packet is traveling this length. So essentially we get 1 plus a little bit of transmission time.
Well, the length of the second time is not gonna be the same amount of the first time, it depends on a lot of
Well,
factors.
if we have packets and they're traveling the same route, then you assume that it's this same length of time.
But we're still talking about the datagram networks, not the virtual circuit, right?
Yeah, these datagram networks. Or any network, it doesn't matter if it's a virtual circuit or not. Because the virtual circuit still sends packets, it just sends them down the same route.
Yeah.
So take the idea, like let's say this is a 1 gig file, right?
Okay.
So the time for it to get to 1 gig is this transmission time plus this transmission time plus this transmission time.
The whole thing.
Because you have to get the whole thing to one device before you start the next one. If you take it and you put in like a regular size frame, right? So like 1500 bytes or bits. Right now the time to get there is the transmission for the first packet to cross this one, right? Which is the width of this network. Plus any little tiny times, which are almost always insignificant in here, right? And then the second packet gets to go immediately following that, right? So we have another 1500 that's following it. So in essence, this entire 1 gig file is the time it would take to transfer that 1 gig file from here directly to there, plus any little bit of stuff in the middle, plus this packet. Does everybody understand that?
Not really. no.
Not really. Okay, so let's.
The last part.
So, because okay, so what I'm getting hung up on is okay. It seems like you're saying that the time it takes to transmit that first packet is the time it actually takes to transmit the whole 1 gig, even though you're still retransmitting it every time. So wouldn't it still be free on either way that you're doing?
No. All right. So let's say our transmission times are 1. Okay? And instead of, let's do something, we're going to use 1,000 packets, or 1,000 bit packets because we're using a 1 gigabyte file. And it just makes easy numbers. 1 gigabyte being 10 to the 12 bytes. Right? Let's make it even easier and make this 8,000 because now that's 8 byte or a kilobyte, right? So we transmit each packet that is 1 kilobyte in size, right? And we gotta transmit 1 million of those to get the gigabyte across. Right?
Okay.
So we have to transmit 1 million. So the first one goes across, right? It spends the time of 1, right? And then reaches here. Then the second one comes across. It spends, now the first one is at time 2, right? And the second one is right behind it. The third one comes across. Now the first one is at time 3, right? And the third one is right behind the second one in the network, right? So our first packet makes it across in time 3.
So in 3 seconds, or 3
Huh?
units.
In
It
3
hit, that's what you're saying.
in 3 units,
3 units.
whatever those is. So that's the first packet, right? When does the last packet arrive?
After
A million and
Million
three.
later.
1,000,003. And that being the 3. Now let's do it the other way. We get 1 gig file, we're gonna send the whole thing at once, right? Whole thing goes across. We have spent 1 million, right? Then it goes across again, we have spent another 1 million. Then it goes across the third time, we spend another 1 million. 3 million.
Yeah.
Plus any switching time in there, which is usually like in microseconds, right? So. Did everybody get it now?
Yeah.
Is there any circumstance where it might be better, instead of using your network, to use a storage device in the regular old shipping system?
Sorry, say that again? I mean, if
So
you
is there any circumstance where it might be better, instead of using a network connection from one place to the other, to use a storage device in FedEx?
So if the
So it's the
application is not time sensitive.
So the application might be not time sensitive, right? The other thing is, what if the data can't be segmented in any meaningful way? So you can't use it till it arrives. Like the last packet needs to arrive before it's useful. Right? Compressed data is a good example of that. Things that are compressed entirely, right? Rather than by block. What other circumstances?
to just have like that much data, like you're something like a petabyte of data.
Yeah.
You can just, I mean, it takes the same amount of time to carry like,
Cross
1,000 tapes rather than 1.
Yeah, so let's use your example. A petabyte of data, right? A petabyte of data is how many bytes?
About terabytes.
10 to the 15th bytes, right? So that is 8 times 10 to the 15th bits. So how long would it take? Let's say we have a fantastic internet connection, right? 150 megabits per second. How long does it take to put that petabyte over this connection?
Well,
Wow.
let's make it that,
What's the math problem?
just basically like divided. That's a long distance.
Yeah.
Yeah.
So we divide 8 times 10 to the 15th
Yes.
over
150 times 10 to the power 6.
1.5 times
Okay.
10 to the
7.
8th, right?
Yes.
8th. Right? That gives us seconds, right? And what gives us seconds why? Right? Because this is
Cancel out,
bits,
yeah.
and this is bits per second, right? So since this is a divide by divide, put that up there, and we get, cancel the bits out, and now we get 8 divided by 1.5, which is what? 3,
Some number.
some number.
Five-ish.
Let's call it, huh?
Like five-ish.
Like, let's just call it 5-ish, because we're doing this kind of math, right? Times 10 to the what? 7 seconds. 5-ish times 10 to the 7 seconds. So 5, 1, 2, 3, 4, 5, 6, 7, right? 50 million seconds.
A million seconds, like 12 days or something like that.
Something like that. It's a, whatever, right? But we could all just break out the calculator or do the exact math. But this might be a circumstance where it's just better to load up a box and give it to FedEx. Not to mention you are tying your entire lineup, assuming that it's that all the way through, your entire that entire lineup the whole time. This is kind of expensive too, type of connection.
So, let's say during store and forward,
Mm-hmm.
what happens if there are other data, other packets coming from another source going to the same router? It does not affect the. So what I'm saying is, if the router is waiting for a whole flow from a particular sender
Okay.
to get to the
So
instance buffer before
there
sending.
could be some issues, and the biggest issue is, let's say you're doing a connectionless type transmission, right? So in connectionless, you're not waiting for an acknowledgement, you're just throwing them in the network. So what happens if this network is, let's just say it's your home gigabit, right? Right, and then your router is Comcast, and it's the good one, right? So it's 50 megabit. So you might run into problems in just simple store and forward, because you could basically fill your router up and it would start dropping packets. But it is the transport layer that takes care of that, so that we can, particularly in a connection protocol, the transport layer is saying, hey, I am ready for the next packet, or I'm ready for the 10th packet, or whatever, right? You can develop an algorithm to where you can get acknowledgments so that you can say, hey, slow down.
Well, we can do that in the at the network layer with the charge packets.
Mm-hmm. Oh, yeah. We want to send, we have money to burn, and so we have a satellite connection to forward information. And we're going to forward information from here to here on the earth. Not quite evenly spaced out. But whatever, we have a satellite network in place. What do we need to know to calculate the latency in this thing?
How many hops?
So we need to know how many hops, right?
Distance between each hop?
Or maybe the average. It doesn't. You don't really need to know the distance between each hop, so long as you know the total distance,
Oh, total, okay.
right? You do need to know how many hops. Why?
There's gonna be some delay associated with each hop.
There's going to be a delay. There is some switching delay, always, right? When a switch enters, or a packet enters a switch, it does not instantaneously find its way out.
I need to know the uplink and downlink.
Huh?
The uplink and downlink speed.
So we need to know the speed of do we need to know the speed for latency? the bandwidth for latency?
We need to know the height.
Oh, we do need to know the height. We need to know the height. Why do we need to know the height? Because it's part of our distance, right?
Yeah.
Yeah.
It's our total distance. So, what else do we need to know?
So I don't need the speed anymore?
So the bits per second, it's gotta be in there, right? You're saying?
No, for just latency.
Just latency.
Just latency. We're traveling through almost a vacuum, so we can just assume that the speed of light is being held,
Mhm.
right? We got some atmosphere to go, but it's relatively short, so we'll just say the speed of light. We need to know that. Speed of light in this class is always just 3 times 10 to the 8 meters. Which, well, I will put, you don't need to write, I'll put the speed of light up on the board or on the test or whatever. Speed of light, C, is this. In this particular case, we need to know the radius of the Earth. Right, which, I'll put it in the test, if this question comes up, is 6,371 kilometers. What else do we need to know?
Why do you need to know the radius?
I'm a little confused on that one myself.
You need to know the radius because this is how you're going to calculate the length.
Oh, okay.
If you're flying through space, through orbits, and you have to get from one point to the other, right? We can make minor, the radius is really, really big, so the arcs here
Is that
are
we're
much
assuming-
different than the actual length.
And we're assuming all the satellites are the same distance from the Earth?
Yeah.
Okay.
And we need to know the height. So whether it's geo, meo, whatever, probably geo, right? But it doesn't have to be. So assuming that you're at the exact right point in something, and the satellite is directly above your source, directly above your destination, so these lengths are the same, right? Then you should be able to calculate how long it takes the latency to get from here to here. You also need switching. Well, I think we said that, right? Which is usually like some tiny, tiny decimal at the end. What's the relationship of wavelength, frequency, and the speed of light?
C equals F lambda.
Huh?
C equals F lambda.
So C equals frequency lambda, right? And frequency is measured in what?
Hertz.
And lambda is a measurement of what?
Meters.
Meters. And speed of light is
Meters per second.
meters per second, right? 3 times 10 to the 8 meters per second. Remember, there's also a little cheat. When you're measuring in kilo versus the speed of light, you can just use a smaller number. If you're using mega instead of speed of light, instead of just using hertz, you can just use a smaller number. Don't have to. Just more things to remember, but it usually gives you a good rough estimate of what your answer is really correct or not.
Can you repeat those again?
So there's cheats, right? So frequency is in hertz, right? This is and C is in meters,
Per
right?
second.
Per second. So that is 3 times 10 to the 8th meters per second. If we change frequency to kilohertz, which is frequently used, right? Then C becomes what?
3 times 10 to the 5th.
Mm.
3 times 10 to the 5th, right?
On top of 3 seconds.
Kilometers per second.
Or we can do 3 times to 10 to the 11 meters per second, right?
Huh?
We can just add the thousands to the power, so we can do 3 times 10 to the power 11 meters per second. Is that right?
We're just changing the units, though, we're not changing the.
We're
Oh,
changing
okay.
units. We're changing units.
Yep, okay.
So if
got it.
we change the kilohertz, we can change to kilometers and just reduce the number,
Mhm.
right? And if we change to megahertz, then we can change to megameters and reduce the power, right? And this is because in networking, kilo actually means 10 times, or 1,000 times. It's actually a power of 10, not a power of 2, as opposed to data. For the test, anything that's measured in data, we're just gonna assume thousands. So not powers of 2, powers of 10. That will make the math way easier. And I'll put that in the test. For instance, in our petabyte, we assumed it was 10 to the 15th bytes, right? The petabyte actually isn't 10 to the 15th, right? Is 2 to the 40th, which is close to 10 to the 15th, not quite. All right. How many bits? If we have 1 megahertz wide bandwidth, and we're going to send a binary data signal through it, how many bits can we stuff in that thing?
How many megabytes?
1 megahertz.
2 million?
What's the second part?
Yeah, it's the same.
I only got
There's
the
two
first
symbols,
part.
two symbols, binary.
Yeah. So 1 megahertz, and we have a 2-level binary signal, right? So we call this 2-level, or sometimes we call it binary. We can send 2 million through it. Why 2 million?
2 level.
Nyquist. Smart guy told us we could. If we had a 4-level,
That'd be megabits. 4 level.
huh?
Should that
Oh,
be
so yes,
megabits?
sorry.
Yeah.
2 megabits per second.
4 million?
If we have a 4-level, how much?
Well, still 2 millions, which is where there's no way to.
No.
No.
It's not 4. Oh, yeah, it is 4. It's 4. Why 4?
It's 2 times the same frequency.
It's 2 times the frequency, but we said it was 4-level. Why is it 2 times? If it's 4-level, why is it 2 times?
Zero,
It's
zero,
basically-
zero.
Oh, yeah.
That's the log.
Right? So essentially, if you want a cheater way to do it, right? This is 2 to the 1st, and so it is 1 times 1 times 2, which is 2. Right? This is 2 to the 2nd, so it's 2 times 1 times 2, which is 4. In a 4-level, we don't really get anything out of a 3-level, except that we can send other carrier signals down it. But we need to do, be able to do if we do a 4-level, right, that allows us to send 2 bits at a time, basically. 0, 1, 1, 1, 0, 0, and 1, 0.
If it's an 8 level, that would equal to 3 megabits per second.
If it was 8-level, it would be 3 megabits per second, because then we could send 0, 0, 0 all the way to 1, 1, 1.
So for the 4 level, it's gonna be 16 megabits, right?
No, it's 4 megabits.
Because 4 is 2 to the 2. You're taking the power
Okay.
So
Alright,
just
so-
think, remember,
multiplied by 2 for Nyquist, and then whatever your bandwidth is.
so we have like this, right? This is binary, where this is 1 and 0, right? If we want to send another bit down there, then we need a 1, 2, 3. So then we have a 0, 1. Well, let's go 0, 0, 0, 1,
1 0
1, 0, and 1, 1. Right? It takes 4 levels to send 2 bits. If we want to send, trying to give these without giving away the actual question, which I'm sure you guys would hate, but.
We'd get over it.
So let's say that we can send 1 bit per second, and we have a network that allows us to send 1 bit per second per hertz. And we want to send 10 to the 6th bits through our network. So let's just start there. 10 to the, one bit per second per hertz, and we want to send 10 to the 6th through there. How many seconds? 10 to the 6th. What if we could change the bandwidth? We can add more hertz. We could add 10 to the 6th hertz as well in 1 second, right? So if per hertz, we have some amount of bandwidth, right?
Oh, okay.
Right. So if we stuck to 1 hertz, then we could send we'd take 10 to the 6 seconds to stand. But if we increased our hertz, like let's say we had some bandwidth that started with 1 micron. So we could increase the hertz, right, to some amount of point to where we could stuff all these things in 1 second. Huh? Yeah. So yeah, 1 megahertz if its bandwidth is in data, right? But let's say we have a wavelength, and that wavelength is 1 micron. What do we have enough information to solve how many microns we need? Huh?
You need to convert it to frequency if you're given a.
You're gonna have to convert it to frequency.
Hypothetically, a question like, if given this wavelength, how much additional would you need to make this time?
Yeah, so hypothetically, given this wavelength, 1 micron, right? What is the bandwidth above 1 micron? Not straddling, because we showed that actually being below it, straddling it, and being above it is way different answers.
What is 1 micron equals to?
Huh?
What is 1 micron equals to?
1 micron is 1/1,000,000th of a meter. So, given that, do we have enough to answer the question? We have to convert to frequency. What's our formula to convert to frequency?
C equals F lambda.
C equals F lambda, right? So C equals F lambda. What else do we need to know? Huh?
How many hertz you have already, so then after you convert to frequency, you find out how many hertz you have.
C.
So we're gonna send, we'll put this 10 to the 6th up here, bits. 1 hertz, bits per second, right?
So we need to convert the 1 micron to a bandwidth, right? Then
So-
we know C, if we know C and we know the frequency, then we can find the lambda.
We're looking for.
We gotta find frequency, right? Because
Oh, okay.
we gotta find frequency because we have a starting point at 1 micron. So what's the general formula though, right? So we're gonna have our something,
Frequency.
right, is gonna equal what?
C over
Well, it's gonna be a range, which is 1 plus lambda, so 1. So we're trying to find that lambda, right? And you'll find out that this 1 really does matter. Why does it matter?
So it's your starting frequency.
Yeah, so what happens as we go down the scale?
Can have lower
Distances
frequency?
The distances get larger, right? So if we were starting at 0.1, lambda would be much bigger, right? If we were starting at something much larger, 100, lambda would be much smaller.
I'm talking about kilohertz versus megahertz versus gigahertz in the frequency range,
Correct.
just reverse.
Yeah, so as wavelengths get longer, then the frequency goes down, right? So we have to consume more.
You make them to like micro become kilo and hertz will be kilo. So that would
So-
make them equal.
We can do that, but let's get the general formula down, right? So we're looking for this number here.
In terms of meters.
In terms of meters, right? Probably actually in terms of very small fraction of a micron, but yes.
Right.
So in terms of meters.
So you convert micron to hertz, add your 10 to the 6 hertz, and then convert that back to distance,
All right.
the lambda.
So let's do it. So how do we convert 1 micron to hertz?
Speed of light divided by.
Right.
Speed of light
3
divided by
times 10
that,
dx
right?
divided by 1 billion.
Divided by 10 to the 6th, right? 1 times 10 to the 6th.
Minus 6.
Negative.
Okay. So now that gives us the frequency at 1 micron, right? Now what else do we need to get? So that's what, by the way?
F1.
3 times 10 to the 14th is our frequency. Right? And then we this is what happens when you type out your equations.
So then F2, which is the edge of the bandwidth, becomes F1 plus 10 to the 6th hertz, right?
Yeah. So that becomes, is this number, right? That's our frequency, and then we need, this is our base, right? How much beyond that do we need? 10 to the 6, right?
So send it all in a second.
Huh?
So we can send it all in a second.
Yeah, we're trying to get, like, we want to be able to send this amount of bandwidth. We want to create this amount of bandwidth. Right? So we get 3 times 10 to the 14th plus 1 times 10 to the 6th.
3.0000001 or something.
So 3 point what? Let's see, there's
Like 7 zeros.
7 zeros. Like that.
Times 10 to 14.
Times 10 to the 14th. Now we gotta get it back to microns.
And then now you divide that by C.
Then you divide that by C.
Or the other way around. Plug it into the equation.
Huh? Plug it in, yeah, plug it in the equation.
So
So you
is
divide
that
C by
plus or multiply?
Huh?
You divide C by that to get like the,
Divide C by this
yeah.
to get lambda.
So how did we get 3.00001?
Because it was 3 times 10 to the 14th plus 1 times 10 to the 6th. 1 times 10 to the 6th is what are hertz required in bandwidth. Right? So our base was 3 times 10 to the 14th. Right? We need to move 1 million frequencies forward of that. So we move forward to that. The deal is that 3 times 10 to the 14th is a really, really big number.
So why do we have 7 zeros then the 1? It's 5 by 10 12 6.
We're adding 1 megahertz to 300 terahertz.
Yeah, you're adding 1 megahertz to 300 terahertz, right? And so, and these aren't the numbers in the problem, right? But I maybe should have picked some easier numbers. I thought, well, we'll just start out with 1 because that's easy, right? Maybe shouldn't have made it, whatever, right? We're adding this really, really small number to this really, really big number, and what you're really looking for is the wavelength. What's the bandwidth here, right? This is what we're looking for.
Essentially 3 times 10 to the 14 divided by 3 times 10 to the 8, or other way around, and it's really small.
It's a really small number. It's 3 times 10 to the 8th divided by 3 times 10 to the 14th.
Test your float capability on your.
Yeah.
Then everyone will get the wrong answer. It's in the float.
So, note to self, have different numbers for the example rather than just doing it extemporaneously. But that's the idea, right? Convert your wavelength to a frequency, right? Then add the frequency that you were given into it, and then convert that delta back into a wavelength, and you will get some very small bandwidth. This also should give you an idea of how much bandwidth is in the spectrum. It's ridiculous.
Especially as you go in higher and higher.
The higher frequency you get, as far as going from into the like infrared and light and beyond that is ridiculous.
That's where the technology capabilities are really fast right now.
Yeah.
For clock speed.
So it's also clock speed, but it's also something else. So, it's also antenna size. So, huh?
All the components.
All the components. So clock speed is antenna size. The problem is antennas need to have some dimension, you assume, right? And there are some wavelengths that you're never going to be able to make an antenna that size, right? Either big or small.
Not in the way we're doing it.
Not in the way we're doing it now. Intel once invented a variable size antenna, but it costs like $2 more than regular antenna, so nobody put it in their cell phones. But it could solve so many problems. All right. Why isn't link state used for inter-domain routing?
What's,
Link state is used for inter-domain routing.
Too many nodes.
Huh? Too many
Right.
nodes, but it was like generally the problem.
To know if that router's alive.
it's not scalable?
It's not scalable. Too many nodes. It's not scalable because it uses Dijkstra. And Dijkstra has many advantages. Scaling is not one of them. It's super linear when it scales.
Is that the N-1
Yeah. Yeah.
when it's discovered?
Yeah.
What about the link
And
state?
each node has to do that, right?
The link state scale very well for the interdomain
Huh?
compared to the distance vector.
So link state scales well intra with an A domain because we keep in small, right? And then distance vector scales well inter domain with an E because it doesn't converge, right? But it scales well as far as creating it. And that's why the border gateway protocol is essentially distance vector on steroids.
Sorry, I should know this, but I always get confused, like trustee and trustor for intra and inter. Which one is local and which one is super? I always-
Internet with an E is big.
Okay. Inter.
Intranet is small, or smallish.
So
Yeah.
Dijkstra
Local,
is good
right.
for intra, whereas distance vector is good for inter, is that right?
Huh? Distance vector, it scales well to very large networks, right? It scales great, it converges crappy. Link state does not scale well, but it converges rapidly. So link state is used for small networks, not necessarily a LAN, but
So intra.
yeah, intra domain, right? Inside the domain.
Okay.
And distance vector, or more appropriately, border gateway protocol, which is distance vector on steroids, is used outside to link all those networks together.
Thanks. Sorry to have to repeat that twice.
And then border gateway protocol is distance vector because it's the same method of propagation is used, but instead of only keeping only keeping the next hop, it keeps all hops, so that you can create a chain of where to go inside the network. What makes BGP really complicated is all policies. Right, so now you have business policies set on top of technical domain, and the border gateway protocol is choosing routes based on business, not based on anything measurable in the network.
But for, as far as I remember, the BGP is we call it like path vector.
Huh?
The BGP, the border gateway protocol is basically that's what cares about the path.
Yeah.
We compare it between the border gateway protocols and the distance vectors.
So distance vector, but BGP is propagated the same way distance vector is. Propagated.
Okay.
But in distance vector, you throw away all previous paths and you just keep track of the next hop as it goes out. BGP keeps all of that. And that's really as far as propagation of how to communicate with all the other routers, and we're getting way into the weeds because none of that's on the test, right? So, how many errors can haming distance detect?
So, what is it?
Generally.
Can detect one.
Huh?
What?
So you have one Hamming code with n bits. How many errors can it take? Correct.
Just the one?
It can correct one. How many errors can it detect?
2.
Two. Right? If you add more, right? If you increase n, right? So now, like, let's say it can you have a Hamming code that can detect 3 errors, or correct 3 errors, then it can detect 4, right? Can only correct for 3.
First router 3, then we can detect 6, right?
Only just one more.
Only one more.
Only one more.
Okay.
So it can correct n minus 1 and it can detect n.
No. You're right. If it can detect or correct 3 errors, then it can detect 6. It can detect n more.
Correct.
Yeah. All right. If you have a CRC generator of 5 bits, you have a 5-bit CRC generator. How many check bits are actually stored?
2. 2.
So we have some generator that's 5 bits, so 10101. And you use it to check some other number. How many check bits are there?
5?
3.
It's not 5, and it's not 3.
60.
So here, let's do it with just regular math rather than binary math, right? So you have some number and you divide it by 3, right? What are the possible remainders?
2.
Huh?
Math
0, 1, 2.
2.
Well, 0 is not a remainder, right? But yeah, 0, 1, and 2, right? So if you are doing binary math and you're dividing a 5-digit binary number into some number, right? How many possible remainders can you have?
And minus
So it's 4.
Because otherwise you could simply write any number you want at the end. It won't matter.
And the number of the remainder equals the number of the check bits.
Huh?
The number of the remainders equals the number of check
The
bits.
number of check bits, yep.
Okay.
So if you had something that's 5, it has 4 check bits, right? If you have something that's 32, you'd have 31 check bits. Oh, this is another good question. That's my generator. How many bits is that?
5.
It's 5, right? What would it look like?
1,
0,
0,
0,
0.
0.
That's your CRC generator?
Yeah. Yeah, CRC term. Sorry, I was in with the last question. What's the bandwidth delay product?
What's what?
Bandwidth delay product.
What's it again?
The bandwidth delay product.
Bandwidth times the propagation speed? No.
We're getting some things in there.
Number of frames that fit on the channel.
That's the number. Okay, sorta. Actually, that's really, really close. Doesn't actually explain the formula, but essentially, I'll tell you right now, it's the number of bits you can stuff into a pipe, right? Before it starts spilling out the other end. That's your bandwidth delay product, right?
So it is transmission time and
Number of frames.
Maybe we ought to look that up. That one's a really simple one, guys. So, for instance,
And what is the bandwidth delay product again?
the bandwidth delay product is, so by definition, not by formula, is the number of bits that you can put into a link prior to the first one arriving at the other side. So if you go look at the formula, it has something to do with distance and something to do with being able to stuff it.
Available bandwidth times.
It's bandwidth times
Time times the propagation
Round trip
speed.
time.
the round trip time. So it's 2 times bandwidth,
2 times.
propagation speed, and length.
2 times bandwidth propagation speed and length.
Yep.
Oh, okay.
This might be where you're having the book would be helpful.
Yes, yes.
It's on 233.
So this is like a TCP.
So formally, it is 2 times the bandwidth times the delay being propagation speed times length. But in reality, it's just how many bits you can stuff inside of the thing before it spills out the other side. You can fill a pipe, right? Before receiving anything. You can actually have a lot of data actually sitting in the middle of the pipe. So if you had a question that was, what's the bandwidth delay product of a line that was, what's the bandwidth delay product of a line that is X long and has 1 megabit per second of bandwidth. And the propagation speed is the speed of light.
Two times C times bandwidth times X.
2 times C times the bandwidth, right? Times X. It's not quite right.
in this case, are we referring to the stop and wait protocol?
No, there's no stop and wait because we're not referring to anything at all other than where you have two links that are directly connected to each other. So if X is our distance, right? How long does it take to get across X?
Distance
Well,
takes,
some D between X to X.
X over C.
one.
X
Yeah,
over
fine.
rate.
It's X over C.
So X over C for what? To get to X?
Yeah. So you have some distance. Let's change it instead of generic. Right, let's say that it is 10 kilometers. Right, the time it takes to go 10 kilometers is 10 kilometers over C.
Gives you time.
Right? And then
Oh, yeah.
that will give you a time. And your bandwidth delay would be what?
2 times that.
It's 2 times that, but why is it 2 times? So,
It's around the third.
because you gotta get around, you gotta have an acknowledgement, right? So your bandwidth delay is the time it takes to get to one side
And
and to come
acknowledgement.
back, right? But to just fill the pipe, right, when stuff starts falling out the other side, it's not 2 times that, right? So keep in mind if there's a question that says, how much data can you stuff in this pipe? Then it's simply bandwidth delay product, but not times 2, because you don't need an acknowledgement.
Yeah.
So. So I was really considering doing an IP address question. I think if I do one, it's gonna be simpler than this. So the easiest way to determine what IP a network is on, or what network an IP is on, is eliminate all the stupid can't be possible ones first. Right? So, if I have a network with a number of hosts connected to it, and so this network is 192.168.7/24. 24 is a nice easy number, why?
Well, we only have the last octet that's for the host.
Yeah,
so we
because
can have-
it lands on an octet boundary, right? So this network right here only includes 192.168.7
Dots.
and then
0 to 255.
0 through 255, right?
Yeah.
So if you're going through a question, it's easy to eliminate. The 24s should be obvious, right? The 16s should be obvious, right? Because they land on octet boundary. So then you're left with only things that don't land on octet boundary. So if I change this to 22, what happens?
Well, it's basically just take the 7, convert it to binary, and the last 6 bits, then find the network address, and we find out how many addresses, then we can
Yeah,
find
we take
the-
7, we convert it to binary. 7 in binary is what?
111.
0111. 16.
Right, and then, so That's our octet. Right, then what do?
Then we have 6 bits of the mask. We can just like 6 ones. Yeah, 0, 0, and 6 ones. Do an ANDing together, then it will find the network address,
Yep, which is?
which is 7.
Still 7.
So in the case where we have 29 that falls on the fonts octet, then we can't assume that it's going to be from 0 to 255.
You're
Then we
correct.
have to use the magic number.
Yes,
Yeah.
yes, but I'm not gonna go that far. If there is a question and I look at this one and it's just, it's a lot. So it looks like that.
Yeah.
So, and it says, hey, you have A, B, C, D, E, and F, which machine is this one on? Pick one, right? So,
Oh, did you mean like for wooden packets?
huh?
For wooden packets?
Oh, it's just identifying what, it's not even that, it's just what, if I give you an IP address, what subnet is this on? A, B, C, D, E, and F. Right, so,
Is it like
You're gonna do the same job, though.
you do the same job, but then, it might be a lot of work for, not a lot of work.
Instead of just saying, you know,
if we have a question like this, is it going to look more like the assignment question? Than the first one?
I will put an IP question on there. I will make it look more like the assignment, because this one's really open. And the other ones are just routing questions that mainly are going to be covered with the homework answers that I'll do the video for. And that's it. So, if it wasn't on the homework, wasn't done in class, or wasn't done in this review, it won't be on the midterm. Unless it's something like, I might give some really easy true-false questions for like a point each.
Fragmentation stuff.
Huh?
Fragmentation stuff.
Yes. But even the fragmentation stuff's pretty easy, right? How do you, what's the general rule for finding what your frame size is?
You send in the MTU on the buckets.
Yep. So we're going to find the MTU on the pathway. So we're going to set a packet size based on our current network, and we set the do not fragment flag, right?
Mhm.
It is forwarded to the first router. If the router can't forward it on because of the next link, it sends an ICMP packet back,
Mhm.
saying, hey, my MTU is whatever this is, which is also smaller, right? And then you send the smaller one, right? And it gets to the next router. If the next router can't forward it, then it does the same thing. What happens if the ICMP fails? Gets lost on the way back.
You resend anyways.
You gotta
don't
resend
get
anyway,
acknowledgement.
right? Because you just assume that the packet didn't make it to the other side, and it doesn't matter why. It doesn't matter that you remember we built our network from the ground up so that if a router just dropped a packet, then the hosts know to resend the packet. It doesn't matter why they dropped it. Right? So if it receives the ICMP, now it knows why and it can adjust. Otherwise, it just does it again. So that's pretty easy. All the other stuff, pretty easy. All right, see you Monday.
Let's
Just curious, is it gonna be just like like 100% scale, or is it like an extra credit for each test?
I'll put points on it because if I do true false questions, they'll be worth less. So if it can correct, so the question is, if you can design a Hamming code to correct as many errors as you want, right? So if you design a Hamming code to correct one error, yeah, I know, right? Huh? Then it can detect two. If you design it to correct two errors, then it can detect four. It doubles it. So the general is for correct n, detect equals 2n. Yeah, very much so. So, yeah. Okay.